Swapping two rows of a matrix feels like a brute force rearrangement. But a single matrix multiplication does it cleanly and automatically. And once we've changed the matrix through elimination, another matrix perfectly undoes that change. Permutation matrices and inverse elimination matrices. These two ideas are the building blocks powering Gaussian elimination. Let's start with the matrix that does nothing, the identity, and see how one small change turns it into a row swapper. Take a 3x3 matrix with rows labeled 1, 2, and 3. Now watch what happens when we swap row 1 and row 2. The permutation matrix P that accomplishes this swap is 0, 1, 0 in the first row, 1, 0, 0 in the second row, and 0, 0, 1 in the third row. Notice, this is just the identity matrix with its first two rows exchanged. Multiplying any matrix by P on the left will swap its first and second rows automatically. The 2x2 identity matrix I equals the matrix with entries 1, 0 in the first row, and 0, 1 in the second row. Multiplying any matrix by I leaves it unchanged. Here's why. Each row of I acts as a selector. Row 1 is the vector 1, 0. It picks out row 1 of whatever you multiply. Row 2 is the vector 0, 1. It picks out row 2. Let's see this in action. Take a generic matrix A with entries A, B, C, D. When we compute I times A, row 1 of I, which is 1, 0, dotted with each column of A gives us AB, exactly row 1 of A, row 2 of I, which is 0, 1, dotted with each column of A gives us CD, exactly row 2 of A, so I times A equals A. The identity selects every row in its original position. This selection idea is the key to building permutation matrices. Let's swap rows 1 and 2 of A equals the matrix with AB in the first row and CD in the second row. Here's the recipe. Take the identity matrix and perform that same swap on it. Swapping the rows of I gives us P equals the matrix with 0, 1 in the first row and 1, 0 in the second row. This is called a permutation matrix. It reorders rows through multiplication. Now let's multiply P times A. Row 1 of P is the vector 0, 1, dotted with column 1 of A. 0 times A plus 1 times C equals C, dotted with column 2 of A. 0 times B plus 1 times D equals D. So row 1 of the result is CD. Row 2 of P is the vector 1, 0, which picks out AB. The final product P times A equals the matrix with CD in the first row and AB in the second row. The rows have been swapped exactly as intended. Now let's multiply on the right. We compute A times P. Column 1 of the result comes from A times column 1 of P, which is the vector 0, 1. The first entry is times 0 plus B times 1, which equals B. The second entry is C times 0 plus D times 1, which equals D. So column 1 of the product is B, D. Now column 2, A times the vector 1, 0 gives us A, C. So A times P equals the matrix B, A on top, D, C on the bottom. Notice that the columns have swapped, not the rows. Here's the key rule. Left multiplying by P swaps the rows, while right multiplying by P swaps the columns. As a final note, for a 3x3 system, there are 3 factorial, that's 6 permutation matrices, 1 for each possible way to reorder 3 rows. We know how to exchange rows. Now let's undo elimination steps. An elimination matrix encodes 1 step of Gaussian elimination. Here's E sub 2, 1. It subtracts 3 times row 1 from row 2. The matrix is first row 1, 0, 0, second row negative 3, 1, 0, third row 0, 0, 1. Notice the negative 3 in the 2, 1 position. That's what tells us to subtract 3 times row 1 from row 2. Now let's apply it to the column vector 1, 7, 4. For row 1, 1 times 1 plus 0 times 7 plus 0 times 4 equals 1. Row 1 stays the same. For row 2, negative 3 times 1 plus 1 times 7 plus 0 times 4. That's negative 3 plus 7, which equals 4. This is the key calculation. Row 2 has changed. For row 3, 0 times 1 plus 0 times 7 plus 1 times 4 equals 4. Row 3 stays the same, so the result is the vector 1, 4, 4. The inverse matrix reverses an operation. When you multiply with the original matrix, you get the identity. Since E subtracted 3 times row 1 from row 2, the inverse simply adds it back. So E inverse has plus 3 in the 2, 1 position, giving us the matrix 1, 0, 0 in the first row, 3, 1, 0 in the second row, and 0, 0, 1 in the third row. Now let's verify by multiplying E inverse times E. The key entry to check is the 2, 1 position. Row 2 of E inverse is 3, 1, 0. Column 1 of E is 1, negative 3, 0. Taking the dot product, 3 times 1 plus 1 times negative 3 plus 0 times 0. That gives us 3 minus 3, which equals 0. The plus 3 and the minus 3 cancel perfectly. Next, let's check the 2, 2 entry. Row 2 of E inverse is 3, 1, 0. Column 2 of E is 0, 1, 0. The dot product is 3 times 0 plus 1 times 1 plus 0 times 0, which equals 1. Computing all 9 entries of the products, the full result is the 3 by 3 identity matrix. The takeaway is beautifully simple. Just flip the sign of the multiplier and you get the inverse. One common misconception is that finding any matrix inverse is this easy. The sign flip trick works only for elementary elimination matrices with a single off-diagonal entry. General matrix inversion requires more work. So this is a special shortcut, not a general rule. Let's highlight this on the left panel. Recall that E has negative 3 in the off-diagonal position, and E inverse simply flips that to positive 3. The rule is flip the sign, and it works only for a single off-diagonal entry. A warning, this does not work for general matrices. Right? Now, on the right panel, permutation matrices also have a simple inversion rule. P inverse equals P transpose. The transpose swaps rows and columns. For our 2 by 2 swap matrix, P equals the matrix with entries 0, 1, 1, 0. Its transpose, P transpose, is also 0, 1, 1, 0. It equals P itself. To confirm, let's compute P squared. P times P equals the matrix 0, 1, 1, 0 times 0, 1, 1, 0. Working through the multiplication, the 1, 1 entry is 0 times 0 plus 1 times 1, which is 1. The 1, 2 entry is 0 times 1 plus 1 times 0, which is 0. The 2, 1 entry is 1 times 0 plus 0 times 1, which is 0. The 2, 2 entry is 1 times 1 plus 0 times 0, which is 1. So P squared equals the identity matrix, swap twice, and you're back where you started. Here's the big picture. In Gaussian elimination, we decompose A into L times U by applying a sequence of elimination matrices and, when needed, permutation matrices. Starting from the elimination process, we can write A equals E3 inverse times E2 inverse times E1 inverse times U. This entire product of inverse elimination matrices is exactly what L encodes in LU decomposition. Each elimination inverse is found by simply flipping one sign, the multiplier's sign. And each permutation inverse equals its transpose. Because every single step has a known inverse, we can unwind the entire process. When row swaps are needed, we use the variant PA equals LU, where P is a permutation matrix. Let's summarize our 2 key rules side by side. For permutation matrices, P inverse equals P transpose. For elimination matrices, just flip the multiplier sign. For example, negative 3 becomes positive 3. These simple inverses are what power LU decomposition. The bottom line is every step in row reduction is reversible. Linear algebra isn't just about performing operations, it's about knowing you can always undo them.